Uh, okay, gang, welcome to CSC 475. Today, what we're going to be doing is we're going to be finishing up Minimax with alpha beta pruning, and then we're going to go on and talk about Monte Carlo tree search. And yes, it's the Mandalorian with Baby Yoda. Okay. First up, let me see if I can share my screen. So last time we had been talking about Minimax with alpha beta pruning. We had started talking about it. We had covered Minimax pretty thoroughly, and we were starting to get going on alpha beta. And I wanted to repeat that, what we had talked about towards the end of class, and go through it in a little bit more detail, and also show you a video that includes code that implements alpha beta pruning. It's short code. The code itself is actually really quite short once you get into it. But it's delicate. It's short but delicate code. So I wanted to have a video that included the code. So alpha and beta are values that basically express the bounds on how poorly you could do and how poorly your opponent could do. And they're based on looking at the information that you've found so far, okay? So as we begin to search the space, the more we search, the more we'll know, okay? And if you update what you know appropriately, and you also you can then use that to decide, I can cut off a particular branch. I don't need to search this particular branch because I know it's not going to change at all the result. So that's the idea behind alpha beta pruning. Alpha is a lower bound on a maximizing node that cuts off a minimization search of its grandchildren. So alpha is a lower bound. Now, when we begin, if A is the root here, the lower bound is minus infinity. Well, you don't have any information. So how low can you go? How bad can things get for A? Infinitely bad. And normally the way we start this off is, this makes sense if alpha is a maximizing node. So normally the way we play is the top node is the computer, all right? It's the I in the algorithm that we're building. And it wants to win. It's a maximizing node. You can easily have the computer go second, and in that case, this would be a minimizing level. But normally, traditionally, you start off with A being the top node being a maximizing node. Now, you'll remember from last time, the way Minimax works is it is a depth-limited, depth-first search. So A will have some children and will pick its leftmost. And now our opponent will be in charge. This will be a minimizing node. But it will have certain moves that it can make. The search algorithm picks the leftmost. Now we're back at a maximizing node. I would be back in control at C. So I will want to maximize. So C will have some children. The leftmost is D, so I'll go to D. And then D will have some children. Now let's say that we are limiting our search to 4 levels deep, 4 ply deep, 1, 2, 3, 4. So if we're going to do that, we're not going to go any further down than 4, okay? And because of that, we have to have a way, since what we would love to do is we would love to be able to search all the way from the start node to the end state of the game and explore every possibility. If we did that, we would have perfect knowledge of the best moves and counter moves that our opponent could make. And if we had explored the whole state space, we could make optimal moves. We could make the best possible moves. We could be the best player. Now, some games are pretty simple, like tic-tac-toe, and if you play tic-tac-toe perfectly, if both people do that, you'll end in a tie. So there'll be no one who will win the game. So I'm not saying if I had perfect knowledge, I would be able to win each time. I am saying that if it's a fair game, I would either be able to win if my player didn't also have perfect knowledge, or I would be able to tie. If we both had perfect knowledge, the game would be boring because every game would end in a draw. Okay, but we don't have perfect knowledge because we don't have enough time to search the whole search space. So Minimax is a depth but limited depth first search. So you can see I'm searching down A to B to B to C to C to D to D to E. And because I'm not going to go any further, I would apply a heuristic function here. Heuristic function is a function that we've developed that will attempt to measure how good the state is. And so our function says E is a 2. Okay. Notice that 2 is better than minus infinity, right? But then we need to look at D's other children. D has a child of F and D has a child of G. And since this is a minimizing node, we're going to choose the smallest of these numbers, which is the 1. So the value of D will become 1 because that's the value of the best move for my opponent will make. It's the move that my opponent will choose. My opponent will choose G with the value of 1 because remember, these numbers are set up as good for the person, good for me. So higher numbers are better for me. The me being the person who started the graph or the computer that started the graph. So of course, I want to win. The computer wants me to, or I want to win. My opponent wants me to lose, so they will win. I want to win. My opponent wants me to lose, so they will win. So in a minimizing node, the best node for this guy is the minimum node, so that's G with the value of 1. Okay. Now at this point, we can take that 1, that value that we got down here from minimizing, right? And we can make that the alpha value of the grandparents of these nodes. So essentially the one that comes up here flows back to C as its alpha cutoff. Now, alpha is a floor. It's a lower bound. So at this point here, C might have 30 other kids, 30 other possible moves you could make from C. But we know at this point that C will never be worse than 1. Why? Because this is a maximizing node here, maximizing level, right? So we're going to take the highest number that we can find here. There may be numbers that come back that are better than 1 so that we wouldn't go to D. But if this guy came back as -2 and this guy came back as -5 and this invisible guy came back as -8, well, this is a maximizing level, so we're going to choose the 1. We can't do worse than 1 at this point. Okay, so that becomes our alpha floor, our lower bound with how well we will do. Okay, fine. Why did we update alpha? We updated alpha because all of the grandchildren of D were greater than our previous lower bound, our previous alpha, which was -infinity. All of these numbers are bigger than -infinity. We're going to take the smallest of those numbers, 1. So the smallest of all of these numbers, if all of these numbers are greater than our current alpha, which was -infinity, If all of these are greater than our current alpha of minus infinity, we take the smallest, and that becomes our new alpha. It's the worst that C will do, okay? So now then, let's explore C's other kids. Let's say C has another child of H. Well, remember, it's a depth-limited depth-first search, so we go to H, and since that's only 3 ply down, the very next thing we do is go 1 more ply, because we always go 4 ply down, and when we get to the 4th ply, we apply our heuristic function, and this comes back with a -3, okay? But since -3 is smaller than the 1 that we inherited from our grandparent, we can say you don't need to explore any other children of H, because H is at a minimizing level. H is going to minimize, and we found the -3. So H might be lower than -3. Maybe this is a -2, and maybe this is a -8, in which case H would become a -8. But that doesn't matter, because in the level above, C controls, and C is maximizing. And since the value that H gets is guaranteed to be no more than -3, we have already found a better possibility, D. So it does not matter what these two nodes give you. It doesn't affect anything, because by the value of I, you already know that C is not going to select H. That's the idea behind an alpha prune. Does that make sense? Are there any questions? I'm looking at chat. Are there any questions? Do you prune I as well? Pruning means that I don't have to visit nodes and apply and either explore their children or apply a heuristic function. So I didn't prune I. I explored I and found that I had a value of -3. I pruned. Prune means to terminate the search of the children of a node. So I terminated the search of H's children as soon as I found a child that was larger, that was smaller than my alpha cutoff. I can abandon the children of H as soon as I find a node that's smaller than my alpha cutoff, than the floor I'm going to take. Now, let's say I had been 8. I would have had to have kept going, because 8 is greater than 1, right? Maybe the next guy I found was 0. Well, then I could have cut at that point and abandoned searching this child of H, because this is a minimization node. I said we're going to let this be 8, and this is going to be 0. Well, between 8 and 0, this guy's going to take 0, but 0 is still lower than the 1 that I know that I can get from going to D. So as soon as I find a value here that is smaller, that is lower than my alpha cutoff of the grandparents of these nodes, I don't have to explore any more of these children. Okay? So that is an alpha cutoff. And I tried to put things in words here carefully. You can get, it's a fairly easy concept, but it's an easy one to slip through your fingers, okay? Because you're having to deal with, I'm minimizing here, I'm maximizing here, I'm taking the smallest of all of these values that are larger than the floor. So there's a lot of this kind of stuff. So I wrote out carefully when you update an alpha value. So when do you update an alpha value? When all of the children, and I'm making this concrete by saying in this case, E, F, and G, when all of the children of a minimizing node, D, possess H prime values that are above, 2, 3, and 1, are above minus infinity, above the alpha value inherited from the child's grandparent, C, Then the alpha value passed back to the grandparent, C in this case, will be updated to be the minimum H value from its grandchildren. It'll be 1. So C's alpha went from minus infinity to 1 here. So that is updating alpha. The other thing that can happen is you don't update, but you prune. When do you prune? When you encounter a child, the first child you encounter, I, of a minimizing node H, where the child I possesses an H prime value that is below the alpha cutoff that it inherited from its grandparent. We now inherited the minus the 1, positive 1. Minus 3 is less than positive 1. Because of that, you then abandon further processing of the minimizing node's offspring, H's offspring. This is known as an alpha prune. A beta prune is exactly the same thing, but it takes place at the opposite level. So beta cutoffs are the exact opposite of alpha cutoffs. Beta, remember alpha was a lower bound, right? Beta is, alpha was a lower bound on a maximizing node, right? Alpha was a lower bound, the worst you could do at a maximizing node. Beta is an upper bound on a minimizing node. Again, it's the worst you can do, the worst choice you found so far. I can say the worst, or I can say best. It depends on how you want to look at it. You're guaranteed you're not going to do any worse than taking this option. Okay, you're guaranteed that you're not going to do any worse than taking the option. You're still looking for better possibilities. It's why you continue to search. But it's like, okay, I've got this in my back pocket. I'm not going to do worse than this. Okay. And if I find a path that looks like it's going to be worse, then I can say, well, I don't have to explore that path anymore. The one I got in my back pocket that I already know about is better. So beta is an upper bound on a minimizing node that cuts off a maximization search of its grandchildren. Beta represents the best already explored option along the path to the root for a minimizer. So here's where we started originally. So betas, if we're using alphas here and here and here, we're using betas here and here. So normally you pass both the alpha and the beta down, but the one you're using is alpha, then it's beta, then it's alpha, then it's beta. It's the one that's active. So if we start out, our beta is plus infinity because it's the upper bound. For a minimizing node, a node that wants to get the number as low as possible, positive infinity is the worst you can have. So that's why it's implemented. It's initialized to that. So while I didn't show the nodes below D and H, these are exactly the same nodes from the previous one. D's got a 1 and H is less than or equal to minus 3. And again, D is a 1, H is less than or equal to minus 3. D has a value of 1, and H is less than or equal to minus 3. Could have gone lower, right? Because it's a minimizing node. You could have found something worse than 3, but 1 and minus 3. So I didn't change anything. It's the same graph. I just didn't redraw those things here. And we're still going 4 levels deep. Okay, so C is a maximizing node, okay? 1 and greater than or equal to minus 3 are both bigger than, are both smaller than positive infinity, okay? So we're at a maximizing node, so we will take the largest of the children, which is 1, and that will become the beta for its grandparent. So the 1, this is a maximizing node. I had a choice between 1 and less than or equal to minus 3. So C would have chosen the 1. That goes and becomes B's beta value. Now, let's say that we're finished with this branch of the tree and we're going to look at B's next child. Well, that's J, right? Which, by the way, will inherit its parents' alpha floor, which the alpha here will be greater than or equal to minus infinity. We're not using it yet, but it got passed down. And then this B here gets passed down as the beta value here, so it's less than or equal to 1. So K's beta is less than or equal to 1. And we go through the minimization here, 5, 10, and 8. Do we have to go through all three of these? Yes, because these numbers are greater than the alpha value of minus infinity. We're going to take the smallest of them. We take 5, so the value here becomes 5. And that's passed up as the alpha value here. I'm doing both the alpha and the beta. I'm showing you the alphas being updated. But here's a beta prune that happens. What's the value of B? Well, the value of B is a beta. The upper bound is less than or equal to 1. What was the value that we got from K? We got 5 because the minimization gave me the smallest. It gave me a 5. Okay, but J is going to maximize. So J has a value of 5. 5 is bigger than my beta floor, right? So while this value could be, J could return a value greater than 5. Maybe this is 10. Maybe this is 20. I don't know. Well, I'm going between 1 and minus 10 and 10. Maybe this is a 10, right? So J could have gotten bigger, right? But I don't need to look at these values because I already know that that if I had chosen 5 here, okay, a 5 or bigger, because this is a minimizing node, it's not going to let you have that 5 or bigger. It's going to make you take the 1. Because B is a minimizing node, it doesn't care that this is going to be 5 or larger because it's minimizing. It's going to take the 1 it already has. So this is a beta cut. We don't need to look at J's other children once we found a K that had a value of 5 that was greater than the beta cutoff from the grandparent of K. Does that make sense? At this point, we would return to A, and the alpha value is still greater than equal to 1 because that's the value that you're going to get from B. You know you don't get the 5 here because there's no way you could get to the 5 because your opponent is control at this level and is never going to select that 5. So the alpha is still greater than or equal to 1. Okay, it looks like a question came through. Cody, don't worry about programmatically. Okay, I'm trying to get you to understand. About numbers, that's arbitrary. Yeah, if you want 10 to be a win and minus 10 to be a loss, that's fine. However you want to set up your heuristic function. Don't worry about infinity. It's just, a very large number, a very small number. Maxent if they were integers, negative maxent if they were, again, if you were using integers for it. Or if you want to put it in a range of minus 10 to positive 10, you can do that too. Okay. Questions about the beta cutoff. Let's look. So updating beta. When all of the children, D and H, of a maximizing node C possess H prime values that are below the beta cutoff, one and minus 3 are below positive infinity, right? So when all of the children, D and H, of a maximizing node C possess H prime values that are below the beta inherited from the children's grandparent, B, then the beta value passed back to the grandparent will update it to be the maximum H value of its grandchildren. The maximum of these is 1. So that's how the beta got set to 1. Beta pruning. When you encounter a child, K, of a maximizing node J, where the child of K possesses an H prime value, where all the children of K possess an H. When a child of K, when a child of J possesses an H prime value above the beta it inherited from its grandparent B, then you abandon further processing of the maximizing node, node J's offspring. This is known as a beta cut. Again, because K had a value of 5 that it got from its children, okay, and because 5 is greater than the beta cutoff, I don't need to look at these other children because this is a maximizing node and it would return at least 5. Now, if K had come back with a -2, right, that wouldn't have been greater than 1, and so I would have to keep going and exploring children. But as soon as I find a child that's got a value, child of J that has a value that's greater than 1, right, then I can quit. I don't have to look at the other children of that node. That's a beta prune. Now here's another very important thing to notice about this beta prune. This did not cut off just one node. It cut off that node and any of its children, just like it cut off this node and any of its children. So what you're pruning may just be a single node, but it may be the root of an entire subtree. It may be 1 node, 2 nodes, it may be a dozen nodes, it may be hundreds of nodes, depending on how far up the tree the cut is occurring. And what generally happens is when you start a Minimax, it has to go all the way to the bottom for the leftmost nodes. But as it starts getting more information, what tends to happen is the cuts start happening higher and higher in the tree. And so let's say that A had a child here. Well, depending on how things went, now we would have to taken that child and then go down a level, go down another level, and do a heuristic application. But depending on how that went, you might be able to cut off most of the work that needs to occur for A's child here, right? You have to at least go all the way down to the bottom to apply heuristic, and things have to start bubbling back up again. But depending on how the numbers work out, you tend to, as you shift, and I'm only showing, like 2 choices here. Like these are like, well, I showed 3 here. But remember, in Othello, you might have 6 or 8 possibilities that you could apply at every level. It'll vary from move to move depending on the board you get. But alpha beta pruning isn't just clipping off a little node here and a little node there. It can clip off whole subtrees, and for large problems, it can dramatically reduce the work, sometimes by orders of magnitude. I can't guarantee you because it depends on how the numbers happen to work out. If the best moves happen to be towards the left of the tree, well then that's good, and you'll end up abandoning more and more as you move to the right. But if for some reason you were really unlucky and somehow everything started with the worst and moved towards the best, it is possible that alpha beta pruning might prune off nothing. It's highly unlikely, but if all of the numbers flipped a certain way, it's possible that alpha beta pruning would never clip a single node. But in general, it'll clip, I hate to put a number on it because somebody will nail me to the tree, half or more of the nodes frequently get clipped. And why is that important? Because it allows you to go deeper. Maybe I would have only have been able to afford, to go 2 levels deep. Because I'm using alpha beta printing, I'm going 4 levels deep, but that's okay because I'm cutting out a lot of stuff. But in a more real world situation, let's say I want to go 6 levels deep and my branch factor is on average 6. Okay, well, maybe without alpha beta printing, I could only get 4 levels deep. But with alpha beta, I can go deeper. Why do you want to go deeper? Because the deeper you go, generally, the better the algorithm does. Because you're going to be applying these heuristics closer to the end of the game. And then when you get within the last 6 moves of the game, you're going to play perfectly because you can now see all the way to the winning states from where you're at, right? So generally, the deeper you can go, the better off you are. Obviously, the deeper you can go and the better your heuristic, the better you're going to play. Other questions? Okay. So what I do next is I work through some simple examples and I go through every single step. Every time I pass down a value, every time I update a value, and when I'm updating, I have that in bold, and when I'm doing a cut, I have that also in bold, and I used exactly the same verbiage that I did here, obviously with the names of the nodes updated, but I used exactly the same verbiage that I did for alpha and for beta here. Well, that's beta verbiage. Alpha verbiage and beta verbiage, so you can see that I'm sticking precisely with the definitions. Okay? Study these. I've already talked for 30 minutes going back through it, but you need to study it carefully so that you can understand it, because I'm going to expect you to do it on the exam. So I give you 2 examples here, and you can read through them. Please read through them, and you can see. I think I did 2 updates here, followed by a cut. And we can just look at it. I'm not going to go through all the verbiage, but we can look at it, right? This would have started off at negative infinity. I come here to B, come down here to E, I get a -10. A -10, a 5, and a 10. This is a minimizing level, so I'm going to take the smallest. I did have to look at all of them because they're all greater than -infinity, right? So because this is a minimizing node, B will be a -10. So A knows the worst it will do is a -10, which is crappy because that's a loss. So it didn't tell me anything other than the worst I can do is lose the game. If you move to B, you're going to lose. But when I come to C, but because I set it off as a -infinity, it did update it to -10. When I come here, right, -10 is the worst I could do, but 2 and -3 are both greater than -10. So I'm going to be updating my alpha again. I'm going to take the minimum here. What's the smaller between 2 and -3? Well, that's -3. So -3 becomes the alpha floor for A. So then I go down to D and down to J. I find a -8. Because that -8 is smaller than my -3, right? I don't need to look any further because this is a maximizing node in D. Because these guys are minimizing, my evil opponent's not going to give me anything better than -8. He might give me something worse if something worse came along, but he's not going to give me anything better than -8. So I don't need to look at K. It doesn't matter if K is 10 or -10. I'm never going to choose D now because the best my opponent's going to give me, or he's going to give me the worst he can. And so the best of those worsts, it's going to be either -8 or smaller. And I already know that if I go to C, I get a 3, right? Or actually a -3. -3 is better than a -10 or a -8 or less. So I'll go to C, and my opponent will, if my heuristics are right and my opponent thinks the way I think, he's going to give me I, which is a -3. Any questions? Does that make sense? Does that make sense? Any questions? Let's see. How would we know if they are minimizing or maximizing if they're not labeled? I should have labeled it. If I don't label, you can just usually assume that the first level is maximizing and the next layer is minimizing and the next layer is maximizing. That's normally how you do it. Although, again, if the that's normally how you do it. Is the top level is maximizing, the next layer is minimizing, etc. Okay. So yeah, I probably should have labeled it, but I didn't. Okay. Let's see. So the next thing that I want to do is show you guys a little video. It's only like 11 minutes long, but it gives a good idea. It'll recap what we've talked about. It'll give another example. And most importantly, it will give you the code, pseudocode, but code for implementing Minimax with alpha-beta pruning. So it does both of those. Now, it won't be completely everything you need, but it'll get you most of the way there. Okay. All righty. Hold on. Am I sharing?
If you want to write a program that can play some turn-based game like chess.
Write a program that can play.
Oh, come on,
But if you
dear.
want to write
Why are you doing this to me? I think maybe I just have to let the ad
that
play.
inspire, messages that forge brighter connections, and emails that get the job done, you need to think about more than just grammar and spelling. This sentence is grammatically correct, but it's wordy and hard to read. It undermines the writer's message, and the word choice is bland. Grammarly's cutting-edge technology helps.
Is this an ad or did I go to another video?
There's a
accidentally?
button to the right to skip the ads.
Yeah, oh, sorry, it was hidden.
One aspect of this is the search algorithm, which is what allows the program to look ahead at possible future positions before deciding what move it wants to make in the current position. This white dot represents some position in our game with the white side to move. To keep things simple, let's say that in every position there are only two possible moves to choose between. We can visualize these moves as two separate branches, at the end of which are two new positions, where it's now, of course, black's turn to move. We can continue expanding the tree of moves until either we reach the end of the game or we decide to stop because going deeper would take too much time. Either way, at the end of the tree, we now need to perform a static evaluation on these final positions. A static evaluation just means trying to estimate how good the position is for one side without making any more moves. For example, a crude approach in chess would be to add up the values of the remaining white pieces and subtract from that the values of all the remaining black pieces. So large values would favor white, while small values would favor black. For this reason, white is always trying to maximize the evaluation, while black is trying to minimize it. So let's start with these two positions on the bottom left. Say we evaluate them and they come out as -1 and +3. Well, in the previous position, it was white's turn to move. And since white will, of course, choose the move that leads to the highest evaluation, we can assign this position a value of 3 as well. Next, let's evaluate these two positions, and so we get +5 and +1. Once again, from the previous position, white would pick the move leading to the highest evaluation, and so we can assign it a value of 5. We've now evaluated both the positions stemming from this position, where it's black's turn to move. Black will choose the move that leads to the lowest evaluation, and so we can assign this position a value of 3. I'll very quickly step through the other half of the tree. So we evaluate these as -6 and -4. White will pick the -4. The next two positions are evaluated as 0 and 9, so white will pick the 9, and between -4 and 9, black will pick -4. At last we've arrived at the top of the tree, where we can see that white should choose the move on the left, since that way, even if black plays the best move, white will still get a +3 position. So now that the basic idea is hopefully clear, let's look at how this is implemented in Toad. We have a function called minimax, which takes in the current position, a depth for how many moves ahead we want to search, and a bool called maximizing player. We begin by checking if depth is equal to 0 or if the game is over in the current position, in which case we return the static evaluation of that position. Otherwise, if it's currently the turn of the maximizing player, which in our example means it's white to move, then we want to find the highest evaluation that can be obtained from this position. So we create a variable called max evaluation and initialize that to -infinity. We then loop through all the children of the current position, and by children I just mean the position that can be reached in a single move. To find the evaluation of each child, we make a recursive call to the minimax function, passing in the child, depth -1, and false, since it will now be the other player's turn to move. We can then set max eval equal to whichever is greater between the current max evaluation and the evaluation of the child position. Once we've evaluated all the children, we can return the maximum evaluation that we found. Now, we do essentially the same thing for the minimizing player, creating min eval set initially to +infinity, and for each child position we call minimax, passing in the child, depth -1, and this time true. Min eval then gets set to whichever is smaller between the current minimum evaluation and the child evaluation, and finally we return the min evaluation.
If you own Apple stock, know someone who does, or have even thought about buying it, there's something you...
Okay, I do not know what's happening here.
Let's step through this example again, this time with the code in front of us. First, though, we'll need an initial call to the minimax algorithm to start things off. Okay, we're at the first position, and we want to find the max of the two children. So we call minimax on the first child. It wants to find the min of its two children, so it calls minimax on its first child, which in turn wants to find the max of its two children, so it calls minimax on the first. At this point, though, depth is equal to 0, so minimax returns the static evaluation of that position. This value gets passed up to the parent, which then calls minimax on its second child, receives the static evaluation from that, and returns the max between the two children. That value gets passed up to its parent, which now calls minimax on its second child. Minimax is called on its two children, getting their static evaluations, and the max is passed up to the parent, which passes the min of its two children up to its parent, which now calls minimax on its second child. I'll stop with the blow-by-blow narration now, but hopefully it's quite clear how the algorithm uses recursion to search through the tree. Now that we've seen how plain minimax works, let's run through this example yet again to look at how it can be sped up using pruning. These first few steps are the same as before, but consider the situation we have after evaluating this +5 position. Without yet evaluating the other position, we know that white can at least get a 5 from here, so we can mark this position as being greater than or equal to 5. We can now see that black won't go down this branch because he already has a better option available. This observation means that we don't have to waste any computation on evaluating this final position. We can simply pretend it doesn't exist. In other words, we've pruned it from the tree. Things now continue as normal again for a few steps until we get here. Black to play in this position will be choosing whichever of the two moves leads to the lowest evaluation. So we know the evaluation here is going to be less than or equal to -4. We can now be sure that white won't go down this branch because he already has a better option available to him, and so we can prune these positions. As you can see, the result of the search is exactly the same as before. We've just saved some time by not considering positions when they can't affect the outcome. Okay, I want to quickly go through a slightly deeper tree. I'll just fly through these first few steps because there's no pruning happening, so it's quite straightforward. In fact, it is actually kind of interesting that we've gone through half the tree and haven't been able to prune a single position yet. So pruning isn't guaranteed to occur. It very much depends on what order the moves are in. Ideally, the moves would be ordered from best to worst for the player whose turn it is in that position. For example, if these two moves had been the other way around, we would have been able to prune the second one. For this reason, it's usually a good idea to order the moves based on how likely they are to be good. For example, in chess, capturing a piece with a pawn is very likely to be a good move, and so it would be wise to explore it first. Anyway, let's continue with this tree. So this next position has been evaluated as +1. And now I have a question. Do we need to evaluate the other position here, or can we prune it? If you're in the mood, I'd recommend pausing the video to figure this one out. So without evaluating the other position, we can say for sure that the previous position is less than or equal to 1, since black is of course just going to choose whichever is lowest. This means that white will never go down this particular branch, because if the best he can hope for is a +1, he'd rather just go the other way at the start, where he's guaranteed a +3. So we can indeed prune that position. Alright, let's finish off this tree. Here we got a 5 and a 2, so black would of course choose the 2. That means this position is less than or equal to 2, and so like before, white will never go down this branch since he can get a 3 by going the other way. This means that we can prune the rest of these positions. The tree is now complete, and we can see that with best play from both sides, the game will follow this path. Let's look at how this pruning stuff works in code. We'll start with our original Minimax algorithm and add 2 parameters called alpha and beta, which will essentially be keeping track of the best score either side can achieve, assuming best play from the opponent. We'll need to update our recursive calls to Minimax to pass on these 2 new values. Now, for the maximizing player, we'll set alpha to whichever is greater between alpha and the latest evaluation. Then, if beta is less than or equal to alpha, we'll break out of the loop. Similarly, for the minimizing player, we'll set beta equal to whichever is smaller between beta and the latest evaluation. And then once again, if beta is less than or equal to alpha, we'll break out of the loop. To better understand what's going on, let's step through the example one last time. In our initial call to Minimax, we'll pass in -infinity, which is the worst possible score for white, as our value for alpha, and +infinity, the worst possible score for black, as the value for beta. These values get passed down until we reach our first end position. Here, -1 is greater than alpha, so the alpha value of the parent gets set to -1. 3 is then greater than -1, so the alpha value gets updated once again. However, beta is not less than alpha here, so no pruning occurs. Next, in the parent position, beta gets set to 3, and this is passed down to its second child. After evaluating this +5 position, alpha gets set to +5, and now beta is less than alpha. Since in this position it's white to move, beta being less than alpha means that black had a better option available earlier on in the tree, and so we prune. Going back up the tree, alpha gets set to 3 in the first position, so we know white is guaranteed at least a 3, but we need to explore the other side of the tree to see if he can do better than that. So coming down here, neither -6 nor -4 are better options for white, so alpha doesn't change. In the parent position, beta now gets set to -4, which is less than alpha. Since this position is black to move, beta being less than alpha means that white had a better option available earlier on in the tree, and so once again, we can prune. We've now completed the tree. So hopefully this video has made sense of the Minimax algorithm and how it can be sped up using this idea of pruning any branches that can't affect the outcome due to the fact that one side will prevent that branch from ever being reached, as they have a better option available earlier in the tree. I'll leave you with the last few moves of this game, which was the first time a computer was able to defeat a reigning world champion in classical time controls.
And that's actually kind of cool that that was Deep Blue versus Kasparov in the first game that Deep Blue won. Cancel. And I see why those ads were coming up, because I'm not logged into my I'm not logged into my personal account that blocks ads, so that's why I was surprised to see those ads coming up. Okay. Let's see. Let's see. Question. When we are talking about the numeric values in Othello, are we referring to the number of the opponent's discs that we can flip for a given new disc placement? that could be a heuristic function, yes. But it is not just the number that you can flip. It would be the say if you're white, it would be the number of white discs after you move and you flip, right? So you want to maximize the number of discs that are of your color and minimize the number of discs that are of your opponent color, and vice versa. So that is one very, very simple heuristic. There are many other much more subtle heuristics that involve things like the positions of the pieces on the board. For example, in Othello, corners are best because you can't flip a corner. All right, so if I can get a corner, it can't be surrounded to be flipped afterwards. So just a count of pieces is a simple heuristic, but a weighted count of pieces tends to be a better heuristic. And if you're wondering about, well, how do I figure out what these weights are? The internet is awash with heuristics for playing Othello, because many professors over many decades have assigned Othello as a game. It's not as hard as chess. It's a little easy. It's a little better than checkers, right? It's an easy game to program. So professors over the years have assigned it, and it's much easier than chess. So you will be able to find examples. One thing that we're not going to go through, but I did want to make you aware of it, is there's another video that's got a very nice it's not as nearly as pretty to look at as the one we just showed, but it's got a very nice example walkthrough of Minimax, but it does it through it's handwritten, so it looks kind of messy here, but basically the guy by hand walks through all of the calculations, and each time the calculations are updated. So I'm not going to take the time to go through it, but you might want to watch it. I would also advise you to go back to the one that we were just looking at here and spend some time with it. The code is really nice. I told you it's pretty straightforward and simple. Now there are some things, you know, he built this thing so that it was just a binary tree, right? There were always two moves from everything. Your Othello is obviously going to have more than two moves from every position, and so it's going to be a little bit more going on there. But it won't be much more than what we showed there. So that should definitely help you get started quite a bit. Let's see. The other thing I wanted to do is I wanted to go through the programming assignment. So here's the programming assignment. So the first thing to note is it's due 2 weeks from yesterday. It's due on Monday the 16th. That's the Monday of finals week, so you got just under 2 weeks to implement this thing. I would strongly encourage you to get started on it today. Now, I know I told you guys on the machine learning one, get started early, and I still had almost nobody did. And I had people begging for extra time at the end. And I'm like, guys, I gave you almost 3 weeks for that one. I consider that one a little bit more difficult. You've got 2 weeks for this one. But get started now, because, you know, towards the end of next week, you're going to get into the press of beginning to study for finals, right? So this week, really for the next week, through about Tuesday of next week, this tends to be the quiet time. We all know there's the quiet time after midterms and before finals spin up. There's a quiet time of about a week or so, and this is it. This is the time to implement this program. You don't want to try to be implementing it the weekend before finals, right? Because you're going to be needing to study for your finals. So get started on it now. We've covered everything you need to know in detail for implementing this. But now let's read through it. So it's due at 9 a.m. on Monday the 16th, so 13 days from now. The assignment will give you experience implementing Othello. Sometimes Othello is called Reversi, and a minute to learn, a lifetime to master. So that's the little instructions there. It's probably best for you to think of the game in 2 pieces. The first piece is getting the game mechanics working, okay? So what do I mean by the game mechanics? That is, how do you represent the board? Well, it'll be a 2-dimensional array, almost certainly, right? Where if it's a 2-dimensional array of characters, you know, W and B, white and black, whatever. Can you use graphics? Yes, you can use graphics. Do you have to use graphics? No, you can use ASCII graphics if you want to. I would recommend getting the core of the game working before you spend time getting it to look pretty. Although I have had some students just turn in absolutely gorgeous games. I think I had one actually even do it with a web-based implementation, so you could play it on your phone or on your or through a website. That was a really nice one. But you know, that was nice, but that person spent a lot of time that they did not have to do. They just got into it, and so they did. But anyway, so you got to represent the board, initialize play, accepting player moves, including rejecting illegal moves. So to be able to play the game, it has to be able to figure out what are the legal moves and only accept a move that's legal. It's got to reject moves that are illegal. Computing the discs that should be flipped, displaying the board after each move. Again, you could use ASCII graphics if you want to. Keeping score, and importantly, recognizing when the game is complete. You got to be able to recognize a win or a loss, you know, or a position where no more moves can be made to be able to declare the end of the game. So that's the first thing that you need to do, is you need to get the game working, okay? The next thing is implement Minimax algorithm with alpha beta pruning and a reasonable heuristic. As I told you, the internet's awash with heuristics. We've gone through Minimax now, and we've gone through alpha beta pruning, and I just showed you a video that shows that the actual code is half a page for Minimax with alpha beta pruning. But making sure you understand that code and can implement it is not, you know, a 5-minute task. For our previous assignment, I had you guys implement in Java and implement MNIST, okay? There are lots and lots of Python implementations on the internet. There are of MNIST. There are very, very few, if any, of it implemented in Java. One of the reasons why I had you do it in Java, and one of the reasons why I had you implement the matrix computations by hand is I know you just can't go out and grab a solution for that. and it was critical that you learn to do it yourself. Othello, the internet is awash with these games, but do not give in to the temptation to take a solution that's out there, okay? Don't do it. You can look at solutions that are out there. You can look up heuristics that other people have used, but write it yourself. Because if you don't, you're not going to be able to get through our little code review session. And that's always, it's only happened, well, it's happened over the years, a handful of times. I would say maybe over all of the students I've done with, maybe 4 or 5 people. But it's really uncomfortable when a student didn't write it, because I start asking questions and, oh, where did you do this? And you start fumbling and, oh, I think that's, oh no, I guess that, and as soon as you're doing that, it's like, you didn't write the program. If you wrote the program, you know where you did everything. And if I ask you, why did you do something this way? You'll say, oh, because blah, 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 and if you didn't write it yourself, you'll just start fumbling. And so let's not go through that, please. I don't like it. You don't like it. And it's not cool. So, and even if you were somehow able to slide through the session with me, you would have cheated yourself by not writing the programs. You need to gain classical gameplay, state space, Minimax. These are all key ideas in computer science, in artificial intelligence, and you need to know them. If you need to know them if you had a course in AI. So please don't plagiarize the program. It'll be obvious and it'll be painful. And I have enough drama in my life. We all do. With COVID, we all have way too much drama in our lives. So let's not add more drama, please. Okay. And now after that, if you do choose to try to pass off a solution, after me literally begging, I would get on the floor and beg, but you wouldn't be able to see because the cam would be pointing too high. But after I have figuratively begged you to do your own work, please do your own work. And if you don't expect any sympathy from me, because there won't be any. Okay. So what are the requirements and the grading rubric for this thing? Your program is appropriately commented, including a comment block at the top of your main program with your name, student number, the date, the assignment number, and a brief description of what the program does. That's worth a letter grade. Comments should also be present throughout the program to explain what each part does. That's worth a letter grade. This is exactly like it was on the previous assignment. Sadly, one of you actually lost a letter grade because you didn't put a comment block at the top of your program. I felt really bad about taking off a letter grade, but not so bad that I didn't do it because it's in the instructions. This is my way of giving you 20 free points, right? But I can lead a horse to water. I cannot make them drink. I can put 20 free points on the table and say, here's 20 free points. Take them, please. Make me happy. But I can't force you to take them. So anyway, number 2, 40% of your grade. Your program implements the rules of the Othello game accurately. In other words, two humans can use your program to successfully play Othello. Details provided in task 1 above. Not this one, that one, right? The legal moves, the board representation, the flipping of discs, blah, 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 blah. That's what I mean there. You got to get that working. If you don't get that working, you're not going to be able to do the Minimax algorithm because there's not going to be anything to Minimax on, right? So the first thing you got to do is you got to get the game implemented. So, It recognizes it can set up the game, it can accept moves, it can reject illegal moves, it can flip pieces, it can keep score. You got to do all that first. It's not that hard, but you got to do it. Number 3, 20 points. Your program implements the Minimax algorithm. The search depth should be easily adjustable, and the program should display. So the search depth should be easily adjustable. It'd be best if you can adjust the search depth from move to move, right? So it's your turn. It would be nice if you could say, on this one, I want you to go to a depth of 6, right? You could set the search depth at the start of the program and always use the same thing, but it would actually be nicer if you could dynamically change the search depth as the game was being played. It'll make it easier for us to look at and grade if you can do that. So search depth should be easily adjustable, and the program should display the total number of game states examined prior to making a move. So when it makes a move, I want it to print out how many states it looked at to make that move. That's important because that's going to give me an idea of how much work it did to come up with that move. Your program should support computer playing either white or black, either moving first or moving second. Note, to demonstrate that Minimax is implemented properly, you should have a debug mode you can switch on a move-by-move basis that shows all of the sequences of moves considered from the current state and the heuristic value associated with each move sequence. This debug mode should be off by default. Note, you will not be able to demonstrate Minimax if you've not fully implemented the rules for Othello first. Well, I said that at the beginning. This debug mode, if we use it, I'll probably use it to look at one thing where I say, okay, set the search to go 2 ply deep, you know, a move and a counter move, and let's see the moves printed out for that, the moves it considered. Much more than that, it just generates a wall of text that's not really usable. But I do want you to have a debug mode. It should help you debug your program if you run into a problem. Again, if you go more than 2 moves deep, it's going to get to be so much that it's not really going to be that helpful to you, but implement it. Number 4, your program should properly implement alpha-beta pruning. You will provide the ability to easily switch on and off alpha-beta pruning on a move-by-move basis. So just like I'm saying that it would be good to be able to show the search depth should be able to be set from move to move. I'm not making it a requirement. I'm saying should here. But on alpha-beta pruning, you must be able to turn on and off alpha-beta pruning on a move-by-move basis. By observing the total number of game states when alpha-beta pruning is enabled versus disabled, you should be able to demonstrate that alpha-beta pruning is operating properly. So I'm not going to have time in our 15 minutes to sit with you and trace all of the moves and the prunes that happen. There's just not enough time. But what I can do is if you're printing out your program considered X number of moves, X number of states, every time you visit a state, you'll add 1 to that counter, right? If you can show me the number of states and then I have you switch on alpha-beta pruning and make the next move go in the same depth, the number of nodes looked at should shrink dramatically, okay? So that'll be how I'll check whether your alpha-beta pruning is working. And more importantly, as you're debugging the program yourself, that's how you can check to see whether alpha-beta pruning is working. Is it dramatically reducing the number of states that you're visiting? If it's not, your alpha-beta pruning is not implemented correctly, okay? And then finally, 10% is awarded if the program is able to beat a human who is really trying to win. This will be demonstrated by showing me a recorded program trace of the entire game. So one of the things your program should be able to do is to write out the board states and the moves that were made so that we could quickly review a game from start to finish. And like I said, if your program is good enough to beat a human, you or me, who are really trying to win, you have to be trying to win. You can't be throwing the game for the points. You got to be trying to win. If it can do that, then you get 10 points. Notice that all adds up to 110. So that this 10% is kind of a bonus if your game is good enough to beat you. By the way, most students who get this program working get that extra 10 points. It's not hard to build an Othello player that's better than a human, especially, I don't think any of us are ranked Othello players. So it's pretty easy to build a game that'll beat you. Or your parents. This will be another thing that you can show friends and parents. It's another fun thing to do. It's almost as fun as the handwriting recognition to be able to show them a program you wrote that's better at playing a game than you are or they are. So it's fun. You must work independently and develop your own code. Sharing a code is absolutely forbidden. You may, of course, look at solutions to this program that are online, but plagiarizing a solution from the internet is strictly forbidden. If you attempt to do so, it'll be obvious. You must be able to explain how your code operates during a one-on-one code review session with the instructor. And if you don't write the program, you're not going to be able to do that. Submitting your assignment for a grade, you'll need to submit 2 separate documents, a copy of your source code and an execution trace of your program playing you in a game of Othello from first move to last. A copy of these 2 documents should be emailed to mike@latech.edu no later than 9 a.m. on Monday, the 16th of November. The subject line should be CSC 475, Othello program, your name, where your name is replaced with your name. So, for example, if Isaac Asimov were enrolled in the class, it'd be kind of hard since he's dead. But if he were somehow enrolled in the class, his email subject line would be CSC 475, Othello program, Isaac Asimov. Does anybody know how Asimov died? I know, this is a Mike side discussion. Does anybody know how Asimov died? As an atheist. He did die as an atheist. That is true. That is very good. Robot attack. Actually, Isaac Asimov died in the 90s of AIDS, when AIDS was an absolute deadly disease. Now, you might say, oh, I didn't know Isaac Asimov was gay. Or an IV drug user. Isaac Asimov was neither gay nor an IV drug user. But very, very sadly, when the AIDS pandemic first started, they didn't know what was causing it, right? And so he had a blood transfusion. That's exactly right. He had triple bypass surgery, heart problem, and the triple bypass saved his life, but the blood transfusions that he got killed him within a few months after that, because there was no test for HIV. People didn't know what it was, so he got HIV from blood transfusions for his triple bypass. I mean, that is just so sucky when you think about it. You go in for a life-saving operation, it saves your life, and it kills you all at the same time, or kills you 6 months later. Really, really sad. Let's see, more comments here. Someone's reading ahead and notices that they can use Python this time. And Zach says, this is a blessing. So, okay, you're getting a blessing from an atheist, but fine. I'm actually an agnostic if you want to get detailed. When you're saying dynamically adjustable, Do you mean something like a constant at the top of the program that we can change to change the depth, or should it be able to change at runtime? What I mean is at runtime, your program should ask you how many ply deep do you want to go, and that should be adjustable. And if it asks after each move, it should be trivial to be able to change it after each move. Because remember, Minimax runs essentially from scratch for every move, right? And Minimax uses the depth, and so should be straightforward to do that. Okay, I hadn't quite finished reading here. You'll be required to meet with me for approximately 15 minutes on either Monday or Tuesday, the 16th or 17th, to demo your program and explain how it works. The sign-up sheet tended to work pretty well. Look, guys, I did notice a few of you did not sign up until like a few minutes before your meeting with me. Don't do that again, because once I have those empty blocks, I need them, because sometimes some people go over their 15 minutes, and sometimes it's nice to be able to take a bathroom break between, and these things stack up. And then if I go, oh, well, okay, I'll have 15 minutes here, and then I get to that 15-minute block and somebody has slipped in a name, I'm like, crap, it's literally crap. It's like, sorry. But yeah, so sign up before we begin. The meetings, don't say, oh, I'll sign up whenever, I'll show up and then I'll just sign up then. Don't do that, okay? Are there any questions about this? Be prepared to demo your program. Did I skip over reading what you could implement in Python? Where did I write that? Oh, you may choose your implementation language. Python would certainly be a reasonable choice. You can use any language that you want. You're going to be running this on your own machine. You're going to send me a copy so I could run it if I wanted to. But if you're most comfortable with Python, or you're most comfortable with C++, have at it. Use your favorite language. I did include the rules for Othello here. It's very simple. Most of you have played Othello or Reversi as a child, but they're the rules. They're very simple. Again, any question? Fortran, Zach, I'm going to hold you to it now, dude. I'm going to expect a program in Fortran. And Tyler, I'm going to expect one in assembly. Okay, now who said binary? Let me hold that person to binary here. Oh! Okay, no, I'm not going to hold you guys to it. I'm joking. But yeah, you can use any language you want. Any other questions for me here? Okay. All right. We've got one more thing we want to cover here. Oh, I've got plenty of time. This is great. Let's see. So, Minimax, with alpha beta pruning, has been around for a long, long time. I think Minimax was actually originally described like in the 1930s, even before we had computers. And even from the early days of computer game playing, Minimax was used as the standard algorithm. It stood the test of time. It's still a very popular. Shannon's paper, according to Eric, was on Minimax in the 50s. That sounds totally correct. Shannon did a checkers playing program, if I'm not mistaken, and it caused a big stir because it was the first time a computer was able to beat a human in a game that humans played actually for fun. So that was a really big moment. Minimax, though, has been, even though it's still very, very popular, it's taught in pretty much every AI course, and it's still quite good, quite useful. The current hot algorithm for game playing, two-player games especially, is Monte Carlo tree search. And Monte Carlo tree search is now the so popular because Monte Carlo tree search is what is used in the AlphaGo series of programs. Yes, AlphaGo uses machine learning, but AlphaGo also uses Monte Carlo tree search. The Monte Carlo tree search algorithm, I want to say, is only like 10 years old. It could have been discovered anytime. It's in many ways it's quite similar to Minimax, but it's only come about in the last decade or so. And one of the reasons for that is for it to be useful, you have to be able to do lots and lots of simulations. And so on slower computers back in the day, it probably would not have performed very well. But if you can throw tons and tons of compute resources at it, it can be better. Now, what's the big advantage of Monte Carlo tree search? Well, like I said, with lots of resources, it can do quite well. But the other real big deal about Monte Carlo tree search is that with Minimax, what is Minimax? It's a depth-limited, depth-first search with a heuristic, right? We use the heuristic to be able to say what to do when you get as deep as you can go, and you can't afford to go any deeper. Well, we use a heuristic. Well, that's good and all, but that means that a human had to program in that heuristic. So that means that a human had to program in that heuristic for that particular game. And so what we want, I mean, you know, we all want an AGI, an artificial general intelligence, right? Well, general. We want something that's general. Minimax, your Othello game that you're going to write only will play Othello. If you wanted to write a chess game, you would be able to reuse the ideas, the basic algorithm for Minimax, but you'd have to have a different heuristic, and it would have to blah, 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 right? So it's not at all general. Monte Carlo tree search, well, why is it called Monte Carlo? Does that mean that we're going to go out and we're going to play blackjack or something, right? We're going to gamble? No. What it means is that we're going to use simulations, and we're going to use statistics derived from those simulations to make decisions. So we're going to do that instead of having a human-crafted, hand-coded heuristic. So you're going to still need the rules, okay, for the game. A human will have to program in the rules for the game. But with Monte Carlo tree search, as long as you've given it the rules, it can discover maybe the best path without explicit heuristics. You might say, that doesn't make any sense to me, Mike. Well, one of the key ideas is that when you get to the frontier, it'll still be a depth-limited search. Monte Carlo tree search is still depth-limited. It's got some characteristics of a depth-first search, and it's got another thing we'll look at in a minute that helps it be breadth-first search. So it will exploit paths in a depth-first manner, and it will also explore in a breadth first manner. And there's an equation that will balance the desire to go deeper versus the balance to look broader. That's built into the Monte Carlo tree search. But when you get to the frontier, instead of applying a handcrafted heuristic, what you will simply do is, in what are called a light play, is you'll generate a move, you'll generate a valid counter move, you'll generate a move, you'll generate a valid counter move, you'll generate a move, you'll generate a valid counter move, and you'll play that all the way out to the end of the game and see whether it was a win or a loss. Now, you're not putting strategy into this play out. You're just legal move, legal counter move, legal move, legal counter move, legal move, legal counter move. So you can do this super fast and play through the game and get to the end and say, did I win or did I lose? And if you do that enough times, okay, you will begin to build up statistics that tell you how good that initial position was. You might say, I don't know if I agree with that. But think about it. If I run 1 or 2 or 5 or 10 games, that's not going to tell me very much. But if I ran 100 or I ran 1,000, I'm starting to build up statistics that give me an idea of whether that starting state was a good state or a bad state. If you're still having problems swallowing this, think about it like this. If I had infinite time, if I could run it an infinite number of times, I would end up exploring all paths and I would have perfect knowledge, so I would have perfect statistics about the accuracy or the goodness of a particular starting node, because I would have explored all possible paths to tell what percentage of them end up giving me a win and what percentage end up giving me a loss. Okay, the Groundhog Day of AI. I like that, yes. And that's exactly what it is. So that's the general idea of Monte Carlo tree search. It's going to be a lot like Minimax, but it doesn't have a human crafted heuristic in it. Instead, it's going to use simulations, lots of them, to generate statistics on how good a node is or how bad it is. And it's also going to have some mathematics that prefer paths that give you better results, sort of depth first, but also part of the controlling function keeps you from just focusing depth first and forces you to look at other options. Because if you didn't do that, once you found something that was better than worst possible, that's where you'd spend all your time. So you need to balance exploitation and exploration, and it balances both of those. So let's look at Monte Carlo tree search. 20 minutes, okay. So this is an introduction to Monte Carlo tree search, and I'm giving you where I pulled this from. That's the web account. Hope it's still good. I didn't check it out right before class today, but Monte Carlo tree search, often abbreviated MCTS, Monte Carlo tree search. Method for making optimal decisions in AI problems, typically move planning. It's used in games. Why is it popular? Because it's been used in AlphaGo. Before I get into this, one thing that I did want to say is we had AlphaGo, and then we had I'm losing it. AlphaGo and is it AlphaGo Plus? It's AlphaGo Prime, AlphaGo Zero. Thank you. Thanks, Jonathan. My brain was misfiring for a moment. So we had AlphaGo, and then we had AlphaGo Zero, and the difference was AlphaGo took, I don't know, a year or a year and a half to build, and it could only play Go, but it beat Lisa Dahl, and then it beat the best human in the world. And then we went to AlphaGo Zero. We didn't, DeepMind did. And AlphaGo Zero taught itself to play Go, and it beat AlphaGo its pants off really, really quickly. And then we had AlphaZero. So we had AlphaGo, AlphaGo Zero, and AlphaZero. And the difference with AlphaZero is it could learn to play different games. You still had to give it rules to do that. But the new thing is MuZero, not Alpha, Mu, MuZero. MuZero learns the rules through feedback. It tries something and you go, not a legal move, and it can learn the rules of it. So you don't even have to tell it anything about the game. It will learn the rules. I guess you have to have a feedback function that tells you whether or not it was a win or a loss in the end, so that it gets some feedback that way. But that's the new one, MuZero, and it's quite cool. You might want to look that up if you're interested in these sort of things. So what does Monte Carlo Tree Search do? Well, it does 4 things over and over in a loop. It selects a node, the best one so far. Okay, and if you start, it would select the best, and then select the best from that, and then select the best from that, and eventually it reaches the frontier. When it reaches the frontier, it will expand the frontier. It will go through expansion, so it will grab a legal move from this node and expand it. So it's just like when you're in Minimax and you explore a child, you open it up, right, and look at that child. But where Minimax would have applied a heuristic, Monte Carlo Tree Search applies a simulation. Move, counter move, move, counter move, move, counter move to the end. And it records whether that was a win or a loss. And it adds that statistic to, well, it takes that win or loss and it updates the statistics of all of the nodes going back to the root. And then it comes back and it makes a selection and does an expansion and does a simulation, backprops the results, and it keeps doing this over and over and over and over. Okay? So again, selection. Starting at the root node, recursively select optimal child nodes until a leaf node is reached. Expansion. If the node L is not a terminal node, i.e. it doesn't end the game, then create one or more child nodes and select one. Simulation. Run a simulated playout from C until a result is achieved. Backpropagation. Update the current move sequence with the simulated results. So it's pretty straightforward. Each node must contain 2 important pieces of information: an estimated value based on simulation results and the number of times that node has been visited. We're going to want to compute statistics that tell you how good a node is. So you need really 2 pieces of information. You need to know how many times did I win going through this node, and how many times did I go down it. If you've got 1 win and you went down at 1 time, that's really good. If you've got 1 win and you went down at 30,000 times, that's not so good, right? So you can think of how many times I won as a numerator and how many times I simulated through this node as the denominator, right? And the numerator over the denominator will basically give you a percentage that says how good that node is, right? From between 0 and 1. If I tried and never got a success, no matter how many times I went down it, I went down it 5,000 times and I lost each time, that's a 0% win. If I went down it 5,000 times and I won 5,000 times, that's a 1, right? A 100%. And of course, you don't expect anything to be a 0 or 100. That's just the limits, right? So node selection. I told you there was going to be a piece of mathematics that was going to help you balance depth first and breadth first search behaviors. And the equation that's usually used is something called an upper confidence bound formula, a UCB formula, an upper confidence bound formula. And you look at it and you go V sub I plus C times the square root of the natural log of cap n over a little n sub I, and you go, oh, math, and you want to run with your hair on fire and go screaming. But don't. It's not that bad. What is V sub I? V sub I is an estimate of the value of the node I, an estimated value of node I. How do you compute it? Well, you compute it with the number of wins that you got going through node I over how many times you've gone through node I. So it's the little statistic that I was talking about a moment ago. This could be as low as 0. It could be as high as 1. Somewhere between 0% and 100%, right? Somewhere between 0 and 1. It's the value of a node, right? So n sub I is the number of times the node has been visited, where win sub I is the number of times you won. So win sub I over n sub I gives you V sub I. It's also this little n sub I here, which is the number of times I visited the node. What is C? C is a tunable bias parameter that's used to balance depth first versus breadth first. So this part, the goodness of the node, influences my desire to revisit that node. It's kind of pushing you in the direction of a depth first search, because I always want to visit the node that gave me the best score so far, to keep running simulations on it to see whether it gets better or it gets worse, right? It's the most promising node that I've seen so far. So let me look at it more and do more simulations. Does it become more promising, or does it become less promising if I keep doing more simulations on it? So that's what the V sub I is doing, because you want to go and explore, to keep exploring, to keep doing more simulations on the best node so far. But if you only did that, you would never look at other options. So this part is what encourages you to go breadth first, to look wider, okay? And it's the square root of the base of the logarithm doesn't matter. You could use log base 10, you could use log base 2. That's just a constant factor, right? So, most engineers and mathematicians love natural log, but us computer scientists, we look at it and go, shouldn't it be a log base 2? If you want to use a log base 2, you can. Nobody's going to smite you for that. It'll work out just as well. So it's a log, okay? CAPN, what's CAPN? The total number of times that its parent of node I, has been visited. So some function of the number of times the parent has been visited over the number of times I visited this particular node. And then we take a square root of it to make it smaller, okay? And again, the C is the tunable bias parameter. If C were 0, since this is a multiplication, you would always go in a depth first manner. You would never look at other nodes. So if you make C 0, basically you're not going to explore, you're only going to exploit. If you make C very large, you're never going to go back to what you looked at before. You're always going to be going and looking at the next new thing. You're going to always be exploring and not exploiting. So you need these two parts of the equation. What's the value for C? A lot of times square root of 2 is used for the value of C. So what about 1.5, 1.4, something or another? So, and we talk about that here. If you let C be the square root of 2, then you could pull the 2 inside if you wanted to and write it like that. And we've already talked about exploration versus exploitation. So exploitation, depth first, going deeper, is controlled by the V sub I, the value of the current node, the current estimate of the percentage chance of getting a win, and the exploration is controlled by this component, which tends to get you to go breadth first. And again, here I'm talking about what I just said of the, when I try to understand what a formula, I'm not a mathematician, okay? If I try to understand, and this can easily look like gobbledygook to me, but what I try to do when I'm seeing a formula first time is I try to say, okay, let me go to extremes and see what happens. So this is a tunable bias parameter. What if I made it 0? What would the algorithm do? Okay, what if I make it a super big number? What will the algorithm do? And by playing with those kinds of extremes of what the algorithm can do or what the equation can do, that's how I get a feel for what the thing actually does. I don't know if that helps you or not, but that's how Mike O'Neill approaches trying to figure out what an equation does. So let's look at an example real quick here. This is for a single player game like a maze search. Starting in node A, I expand each of its children, B, C, and D. And then as I expand B, I will do a simulation. And this simulation is a win. We'll say I got a success, I won. And this is the first time that I've run through here. So I tried once and I got a win. We then now go and look at C, so because I got to explore all of A's children. Oh, I didn't win, so a 0 out of 1. And I tried D and I didn't win either. You wouldn't expect really to win most of the time. It's just one run through. But what's the value of A? Well, I did from A to B simulation, from A to C simulation, from A to D simulation. I did 3 simulations. Basically, you can add up these numbers. 1 plus 1 plus 1 is 3. And add up the numerators. 1 plus 0 is 1. So the value of A is 1 over 3. I've run 3 simulations through A, and I had 1 win. So what do we do next? Well, we plug the values for B, C, and D, the children of A, into the upper confidence bound formula, and I do the math for you here, and we see that we get a 3 for B, and a 2 for C, and a 2 for D. So I want to take the best of these, so I will go now to B, and I will open up B, and I will explore its children and apply the UCB formula, the upper confidence bound formula, its children. So let's do that. B happens to also have 3 children. E, I run it, I get a win. F, I run it, I get a loss. G, I run it, I get a loss. So 1, 2, 3, you might say, oh, why is there 4 here? Because I've already gotten the statistics of 1 win and 1 simulation through B. So I have to update this with the values that I got here. So I already had a 1 over 1, right? 1 plus 0 is 1, but I already had 1, so that's where the 2 came from. And 1 plus 1 is 3, but I already had 1 through there, so that's where the 4 came from. So at this point in time, I have run 4 simulations through B, right? And 2 of them were successful. The one simulation that ran from B all the way down, and then when I explored its children, the one that ran from 2. So right now you look, we back this up here to A. A has 2 out of 6. Why does it have 2 out of 6? Well, because 4 plus 1 is 6, and 2 and 0 is 2. Those backed up to A. A is worth 2 out of 6. Now you might say, well, gee, I should keep going with B because I've got a 50% chance of winning with B. I've got a 0% chance winning with C, and I got a 0% chance winning with D. Well, yeah, but you've looked a lot more at B so far. You only did one little simulation through C and only one little simulation through D. So this is where our upper confidence bound formula comes in again. We will, all of the nodes in the frontier, E, F, G, C, and D, we will compute, well, the new ones, let me recycle. So we have to apply the upper confidence bound formula, again, starting back at A. And so A's 3 children are B, C, and D. So you have to start back up at the top again. So you apply the upper confidence bound formula, but now for B, it's 2 out of 4, and that'll gives you a 1.8. C gives you a 2.68, and D gives you a 2.68. You might say, well, how did C and D's values change, Mike? They used to be 2 and 2. That's right, but remember, cap in how many times your parent was visited figures into the equation, right? That natural log of 6, right? So that can change C and D from the last time you looked at them. Okay. Take the biggest. Well, C and D are both the biggest, but in this case, we always just, I always go from left to right, okay? So we'll do C. Now, what I have written here in red is does not get computed. It would be an error to do so. I almost slipped up and computed them, right? But we don't do that because you start back at the top each time and look at the children, and whichever one gets selected, you look at those children, et cetera. So you start from the top each time. So I put them there, but I said, hey, you know, why don't we do this? Well, the main reason is that the UCB scores are defined from the starting node, and you're not starting at node B, you're starting back at node A each time, okay? So, well, I said I was going to go left to right. I lied. We chose D instead. But D has one child. It's H. It led to a loss. Okay, so now I've been through D twice, and I've been through A 7 times, right? And so see how those numbers got updated? So what do you think the upper confidence bound formula is going to do? Plug the new numbers in for B, C, and D, and lo and behold, as you would expect, C is the highest. Notice what we did. We went depth first for a while, and then the second component of the equation came through, and now we're doing a little bit of exploring of other paths. So we explore C. Oh, did I do it? No, I didn't do it. But you would have explored C, and you would continue onwards from there. Okay? So that's Monte Carlo tree search. I see I'm pretty much out of time. I do have some more notes here. I think I've covered enough. One of the things oh, here's what I wanted to show you. 1928 was when Minimax was discovered by von Neumann. And this Monte Carlo tree search wasn't until, well, I said 10 years ago, I lied, 14 years ago. 2006 is when this algorithm was first written down. You might want to check out Monte Carlo tree search for 2-player games. It's exactly like what we've talked about, except that there's a minimax aspect to it where what are wins at one layer are considered losses at the next layer. So if I won 2 out of 3 here, 1 out of 3 here, and 0 out of 1 here, I went through 3, 6, 7. So that's where the 7 comes from. You might say, well, where did the 4 come from? 2 plus 1 is 3, Mike. Yeah, but the wins here count as losses here. So I lost 2, I lost 2, I lost 1, right? I lost 1? No, I lost 1, which turns into a win. So that was a win. But I lost 2 and I lost 2. So that's how I got 4 here, Michael. I won 2, I lost 1, I lost 2, I lost 1. 1 plus 2 plus 1 is 4, Mike. I'm sorry, I have to go back to first grade a lot of times. But anyway, so yeah, what were wins here become losses, and it just flips at each level. But as long as you do that, everything else is exactly the same. I go through, and you can trace through and see how it works, and that's fine. But it's almost no different if it's a 2-player game versus a 1-player game. So I'm going to call it quits here. Are there any questions for me before I kill the recording? Would this be similar to some statistic-based machine learning? Absolutely, Eric, yes. It is. That is exactly what's going on there. So this is not a neural network, but you're using machine learning, right, by running those simulations and updating what it knows based on statistics. So you can have machine learning that's not neural network based. That's not based on a model of the brain. Do we have any other questions about this? Any other questions for me? Okay, everybody should get started on your programming assignment, and I'll see you guys on Tuesday. Go vote. Go vote. Go vote. Please go vote if you haven't done so already. And with that, I'll end the recording. I'll stick around in case you have some questions to ask, but have a good day.